My name's Tariq. I'm from the UK, in Bristol, and I work for Codasip, as you can see here. And because I'm British, I say Z and not Z. Hopefully you can understand that. Sorry. So ZC has been a very long journey. It's taken several years to get to the point where we had something which everybody could agree on. It's maybe 5 years, I think, before we got something properly ratified. So it's been a big, complex task, but we've got there, and it was ratified in the spring. And it's really good that there are commercial implementations available and commercial tool chains, and this is all wonderful. It's a culmination of many years' work and many, many contributors. So what did we do? So the first problem was that the existing C extension uses up a lot of the 16-bit encoding space. So we started off by dividing it into 3 subsets. So there's ZCA, which is all of the instructions except for the floating point loads and stores, which are the unpopular ones because they don't get used very often and they take a lot of encoding space. There's ZCD, which is double precision, floating point, loads and stores, and ZDF, which is a single precision. And then we created 3 new extensions. So there's, the top one is push pop, the second one is table jump, and the last one is ZCB. I'll go over what's in that in a second. So a little bit more detail. So ZCA is a C extension excluding all floating point loads and stores. ZCF, which is only valid in RV32, is the single precision floating point loads and stores, including the stack pointer relative versions. This slide is quite boring, but I need to keep going. ZCD is the double precision floating point loads and stores. Okay, so to get enough encoding space, we started repurposing some of the double precision floating point loads and stores, and we used that to get the encodings for ZCMP and ZCMT. So the encodings are reused, and then we have ZCB as well, which only uses reserved encodings, so can be used on all implementations without a problem. I presented this slide in Barcelona in the summer. Since then, the spec has moved forward a little bit as the toolchain implementation has moved forward. So we've added new implication rules. So if you specify C, you now get ZCA plus the other bits if you have floating point. And we put some rules in about how you set MISA.C. So really just sort of dotting the I's and crossing the T's on the specification. All the instructions are the same. So ZCB, so it's either 11 or 12 lines added to your decoder. One of the instructions is RV64 only, zero extend words. It includes an RVA23. It's completely trivial to implement because you're only expanding 16-bit encodings to existing 32-bit encodings. So there's really no effort to it, and a little bit more verification than you might have to do. So you're getting half to 2% of code size saving for really, really low cost. So everybody should be implementing this all the time. There's no reason not to. You've been told. Okay, and there's a quick instruction summary. I'm sure the slides will be shared afterwards. The point is I'm trying to show, I'm trying to show the expansion. Sorry. That's a loud cough. I'm trying to show the expansion from the new encoding to the existing instructions. So quite dry, but the only thing there that's sort of interesting is C.not expands to X or I against -1, I think. Okay, so moving on to specifics. So ZCMP targets push and pop, so function prologues and epilogues. And something that typically happens after the function prologue is you will move your argument register, move your A0 and A1 registers to set up the arguments for the next function call. and that typically happens before the function epilogue as well. So we added instructions to optimize the save and restore sequences and for the register moves, reusing encoding space. So here's quite a long example. This is taken from straight out of my spec. So you see, I wonder if this works. That work? Yeah. So you see, so this is mbench picojpeg, the process markers function. So this is what you get for your function prologue. So you've got a lot of instructions. And they're very regular. So you're storing R0, then S0 to S11. I don't know why these are down here and not at the top. And what we do is we map this onto the cm.push instruction into these 14 steps. So the same instruction will expand into those 14 32-bit instructions. So one 16-bit instruction in, 32-bit instructions in. 14 32-bit instructions out. So something that's been available in the toolchain for a very long time is msave-restore, which is where you call a function and you say, in this function, I want to save my registers. So that's already in the toolchain, but this does have disadvantages. Firstly, you have to jump there, you have to jump back. It does the stack pointer increment more than once because it does it for every block of 4 registers, so that's wasting performance. And it uses more code size as well, especially if the function you're calling is more than a megabyte away because the jump to get there on its own is 64-bit. So we started off with 28 bytes. msave-restore will either give 6 or 10 bytes depending on how far away the function is. And then cm.push will always give you 2 bytes. And the encoding is shown at the bottom there. So you have the register list and the total stack adjustment. And we have a sort of quite a good definition, I think, for the memory that's stored, because you can take an exception. Any of the stores could cause an exception. So unlike the vector extension, we don't have something like vstart saying I got to a certain point, and then after I come back, I'm going to resume because I may have crossed a page boundary. What we say is that you will always re-execute the whole instruction. So you can store any byte in that block. It doesn't matter where the exception is. And when you re-execute all of the stores, and then all the memory is updated again. So it has slightly special memory semantics to make the implementation easier. And it means you can optimize it more as well. OK, so the reverse is the return pop-ret, this with a z at the end because it's returning 0. So it's from the same function. So load 0, store a lot of registers, and then return. So this maps onto 16 32-bit instructions. Well, actually, sorry, 16-bit instructions. 32 bytes in total. And again, we get that down to 2 bytes. So this does exactly the same thing. And if you exclude the z on the opcode, then it doesn't move 0 into the return value. That's just an extra saving because it was the most common return value that we found. OK, moving on to, so this one are called table jump. So the idea is that you have a table of your function pointers in memory, and then when you want to jump to them, you have a 16-bit encoding which indexes the table, and then you jump to the table. So you have 16-bit encoding with the table index, and then you jump to the table. So what we found was that if your executable is greater than a megabyte, then your jumps frequently start to take 64 bits to get to the destination. And the example shown there was in the V8 JavaScript engine when we were benchmarking this, one particular debug symbol was just everywhere throughout the code. So just a single table jump would have reduced the executable, which was about 3 megabytes, by about 400K. So in certain circumstances, it's very useful. So some more details here. So we have the table in memory. Indices 0 to 31 have the addresses, but you don't link if you jump to them. And 32 to 255, if you jump to them, then you do link. It means that if you call the same function with and without linking, you need 2 entries in the table. But that case doesn't happen very much, so we didn't optimize it because seems sort of wasteful. And okay, so this points out that because we're reusing coding space, there's still plenty left. So there's much more we can do. ZCF is only suitable, ZCF is only available on RV32. So ZCD is available on both, so there's still plenty of space there. Plenty of room for future instructions. Okay, so we've implemented this in our Codasip toolchain, and all the results which were used during the TG were done using an analysis script, but we have some real results, which is always good to see. Slightly small chart, I suppose, but I think some of them are above 25% and sort of 16% reduction on average. So that's enabling all of the 3 extensions. I'll leave that up for a few seconds. There's quite a lot of detail on there. But again, the slides should be shared afterwards, so you'll be able to study it. Okay, so let's take code size a bit further. So another technique which we've implemented is dictionary compression. So table jump has a table of function pointers. The dictionary compression or instruction table has a table of 32-bit instructions which are commonly repeated. So, for example, you can have a load with a specific immediate value, which is too big for a 16-bit encoding, and that is repeated many times in the executable. Then you can put that in the table and then just have a 16-bit instruction, which will then fetch the 32-bit instruction from the table. So it's a well-known technique of dictionary compression. It's nothing particularly new, but it's very useful, and we have it in our LLVM compiler now and our implementations shortly. So again, mbench, it's too small to show it off properly because the executable is very small, but we have one result, which is very good there. So we ran some bigger code. We did sort of Zephyr and FreeRTOS. Actually, the next slide shows it slightly better. So this bar is showing what you get if you enable the ZC extensions, and this bar is showing what you get if you also enable instruction table. So you're getting an extra 3% on Zephyr and sort of 9% up to 15%, so about 5.5% extra on FreeRTOS. For something that's fairly cheap and simple to implement, I think this is pretty good. Okay, so it's a bit of a marketing slide. That one is from a marketing person. I apologize. It's true. But obviously, the intention was always to be better than the incumbent architecture. But I think instruction table gets us far enough now to be better. So it puts us in a good situation. We have space for more compressed encodings, and anybody who works in embedded systems knows that it's really important to get your flash size down, your memory sizes down, your cache sizes down, and so on, because it reduces the system cost. And note that ZCMT table jump isn't planned until LLVM 18. We have it in our compiler, and actually IAR have it in theirs as well. Okay, so now on to some work we did with Qualcomm recently. So we know that there's the sort of discussion going on about the C extension and the sort of suggested replacement. Alan's nodding. So there's the sort of ZIX, which is the idea behind that is to have 32-bit encodings, which will remove the need for 16-bit encodings, so the decoder and the machine become simpler. There was a statement made that it was too difficult to add it into the compiler. And it's actually, I haven't counted the instructions. It was implemented by my colleague Zdenek in the middle there. You can wave. So next slide's about him. Do you know how many instructions it was, roughly? Yeah, okay. I mean, it wasn't simple. So after 2 days of Zdenek's time, we had all of the instructions modeled in Codal, which is our processor description language, which means that they're automatically added into our LLVM toolchain. So 2 days effort, and they're all in the tool chain. And we had results comparing RV32 IMC, the standard platform, with C replaced by ZIX instead. So the comment here is that all the instructions were in. Some of the instructions need more work in LLVM. So the pair load store weren't inferred terribly well, and PC relative loads aren't supported by the linker. But this is because they're not in LLVM. That's not a limitation of our technology. But the other instructions were modeled correctly and do work. So register loads and stores, pre and post update loads and stores are all fine. Conditional branches and paired moves, which had a peephole optimization. The results we got on mbench are behind what you get with C, but we're working on synchronizing the call mark results between Qualcomm's analysis script, or will be next week, and what we get. So the idea is to try and close the loop on this. So the point of this was it's very easy to add instructions into our tool chain by using our processor description language. The results we got, some of them were very good, some of them were limited by what's in mainline LLVM. So you can't just add anything. It has to be implemented in LLVM. I think that's it. Thank you. Cool. How long was that? 60 minutes.
We have 4 minutes for questions.
Okay. Hi, Jeremy.
Thank you. I should declare an interest because I've worked with Tariq on this for years. When you looked at the mbench performance, I think you were comparing against just plain compiler. What was the speed up if you had save restore in there as well?
None of that was about performance. That was all about
code size. I mean size performance. Sorry. How was the code size saving if you did have the software saving in there?
We probably have some figures somewhere, but I can't remember. But I think, again, the big problem with msave restore was when we used it for a real application, the functions were so far away, we ended up with 64 bit calls.
Yeah, it's great for mbench, but it's not great for if you're doing
so on a real application, it made a big difference. For mbench, it wouldn't make as much difference.
Okay.
The mbench is small with not so many function
thank
calls.
You.
More questions?
Can be dumb question, but is there any patent review for this idea? I mean, this is new instruction, but it is not the new instruction in the CPU market. The prior CPU vendor may have similar idea, and they may have some patent for the protection, right?
For the instruction table?
Yes.
It's based on, there have been implementations at least from the 1990s of that particular technology. So it's old technology.
More questions? We have time. Anyone? Alan, question? No? One. It's hard.
You didn't say the size of the table that the instruction lookup table supported. I mean, you specified instruction, you didn't specify the depth of the dictionary, and I wonder why that didn't make it in the first revision. I mean, why was that kind of left out?
I probably should have put another slide in there, shouldn't I? I think it's 10-bit, so 1,000 entries.
Okay.
We have time for one more question.
Yeah, the slide was missing. I should have added that.
Any more questions? No? So thank you very much, Tariq.
Okay, thanks.